Okay, so this is problem 865, and we're given several things. We know that the friction between A and C, so this block A and C, is 0.3, and we're also given that the friction between the coefficient of static friction between B and D is 0.3 as well, so on the wall here. And then the coefficient of friction between the two blocks is 0.4. We're told to neglect the weight of the wedges, each of the wedges here, and what we're trying to find is the smallest P, this horizontal force P, to lift the load. Okay, so let's get started. Now, what we need to do is break this thing into two kind of parts, right? We need to analyze the top wedge and we need to analyze the bottom wedge. So let's start with the top wedge here. So I'm just going to draw this top wedge. All right. Okay, and we know that it's 15 degrees between those two, which then makes this angle 15 degrees. Okay, and we know that up on top there's 3,000 pounds. We're going to have a normal force at the wall D here, and we're going to call that ND. And then we're also going to have a frictional force. All right. So as we push in here, it's going to want to raise this block up, block B, and so the frictional force is going to be opposite of the motion. So we're putting that down, and the coefficient of static friction there is 0.3 times ND. We're going to have a normal force that the block A is exerting on block B. So we're going to have this normal force. I'm going to draw that upward. Call that N. And then lastly, a frictional force here. And that's going to be equal to the coefficient of friction between the two blocks, 0.4 times N. All right. So notice that this N is different than ND. Okay. Notice that there is a difference between those two forces because we're going to refer to this as N and this is ND. Okay. All right. So let's get to our equations here. Let's first sum the forces in the x direction and set those equal to 0. Okay. So we have this 0.4 times n, and it's just going to be a component of that in the x direction. That should be cosine of 15 degrees. Okay, and next we have this force in here is also going to have a component in the x direction. And from vertical here, let's see if I can draw this. This angle here between this force is also 15 degrees. So that is going to be plus in sine of 15 degrees there. Sine of 15 degrees. And then we have ND pointed in the negative direction, and that should be all the forces in the x direction, set those equal to 0. If you want to multiply these out, we turn out this turns into 0.6452 n minus nd equals 0. Okay, and let's do the sum of the forces in the y direction now and set those equal to 0. So in the y direction, we have this force N is going to have a component in the y direction. So we have N, and this time it's going to be cosine of 15 degrees, and that's in the positive direction. This this frictional force 0.4 N is also, and that's going to be in the negative Y, so we have negative 0.4 times N, and a component, it's the component of that, which should be sine of 15 degrees. All right, and then we have our 0.3 ND here, so that's negative 0.3 ND. And then lastly, our 3,000 pounds, which is on top, setting that equal to 0. And I believe that comes out to 0.8624 times N minus 0.3 ND minus 3,000 equals 0. So we have this equation and this equation here, and solving those simultaneously, we can then get N and ND. So N comes out to be 4485.4 pounds, and ND comes out to be 2,893.9 pounds. Okay, so we have those equation or those forces now, and now we need to move to our second free body diagram. And our second free body diagram is going to look like this. So this is our bottom block now. Okay. Now I want to be careful about how I draw the normal forces here. We're going to have that N force directed downward this time. So if we add these two free body diagrams together, the forces should cancel each other out. So we have N kind of downward this time instead of upwards, how we drew it on the first diagram. And then our frictional force here is going to be placed to the left. We should be able to, so we have 4485 as our normal force, and 4485.4 times our coefficient of static friction between there is 0.4. We know that this is 1794.2. Okay. And then we have our normal force down here. And that is going to be what we're going to call NC. And then we have our frictional force here, which is 0.3 times NC. And do we have any? Oh, we have our force P over here. And likewise, we know that, well, this is 15 degrees. And then this should be 15 degrees up here, 15 degrees there. Okay, so we have all the forces on there, and now it's just doing our equations of equilibrium. Let's sum the forces in the y and set those equal to 0. So we have NC upwards. We have our frictional force, or our normal force here, and that should be in the negative direction. All right, so that's negative 85.4, and that should be cosine of 15 degrees. All right, and then our frictional force, and that will be in the positive direction. So we have 1794.2, and it's just a component of that, so that's sine of 15 degrees. And those are all our forces in the y direction. Okay? And let's move on to doing the sum of the forces in the x direction. We have P, which is positive, and we have negative 0.3 times NC, and then we have a component of this one here, this 1794.2, and that should be negative 1794.2 cosine of 15 degrees. And then we also have the normal force here, and that should be negative, which is 4485.4 sine of 15, and that is equal to 0 there. Believe I got everything. So in this first equation here, we can solve directly for NC. NC comes out to be 3868.2 pounds. And then subbing this in here, we can solve for P. And P comes out to 4,054 pounds, which is then equal to 4.05 kip. All right, and that is our answer for this problem.